Hello everyone, my name is Vidish Kumar Kasanagottu. I am from CSC Cybersecurity B section. Today my topic is independent vector analysis in mathematics. Independent vector analysis. Independent vector analysis is a new approach to independent component analysis denoted by ICA. By extending the formulation of univariate source signals to multivariate source signals. The new approach is termed as independent vector analysis IVA. In the model, we assume that linear mixing model exists in each dimension separately and the latent sources are independent of the others. In contrast to ICA, the sources are random vectors, not just single variables, which means the elements of a random vector are closely related to the others. Thus, we assume the dependency between the elements of a source vector. In this manner, we define dependence between vectors as Kullback-Leibler divergence, commonly known as KL divergence, between the total joint probability of vectors and the product of marginal probabilities of vectors. Then, the model allows independence between multivariate source signals represented as random vectors and dependence between the source signals within the vector representation. The proposed vector density model can, for example, capture variance dependencies within a vector source signal. There are several applications of this new formulation. In the separation of acoustic sources, the algorithm mitigates the permutation problem. That is, the usual ICA algorithms applied into the frequency domain mixture data suffer from the unknown permutation of the output signals. Although there are several engineering solutions to fix this problem after the ICA stage, the proposed method provides a natural solution to the problem by capturing the inherent dependencies of the acoustic signals. It therefore avoids the permutation problem and allows the separation of sources in very challenging environments for many sound sources. Independent component analysis ICA is a computational technique used for extracting the source signals from an observed mixture of multivariate signal. ICA is a special case of blind source separation. Popular example is the cocktail party problem, in which the objective is to detect the speech of different people where a group of people are talking simultaneously. Even though humans can handle this task easily, this is a challenging problem in signal processing. ICA is used for source signal separation in many applications, including medical data, audio signals, or optical imaging. Data can be in the form of images, sounds, or other time series data. ICA can be applied as a dimensionality reduction algorithm because after extracting the source signals, the unnecessary signals can be removed or deleted. ICA is considered as an extension of the principal component analysis PCA, but PCA tries to find the axis that maximizes the variance using second order statistics, while ICA tries to maximize the independence between source signals using the higher order statistics. There are two sources S1 and S2 which produces some signals. Sources are linearly mixed and form X1 and X2, which by using independent component analysis can be recovered as U1 and U2, which are original signals. The observed signals Xi are known. The source signals and mixing coefficient matrix are unknown. Our goal is finding the unmixing matrix W that will give best approximation of S. ICA problem formulation. Let us assume we have m independent source signals S1, S2, Sm. Each source signal consists a sequence of uniform time intervals Sj equals to Sj1, Sj2, Sjn. S is a column matrix S1, S2 up to Sm, where S belongs to real numbers m cross n. S equals to x1, x2, xk is equals to As, where x belongs to real numbers k cross n, a belongs to real numbers k cross m. A is the mixing coefficients matrix. Properties of source signals. We make three assumptions about the source. Signals independence. The source signals are independent, however, their signal mixtures are not, as they share the same source signals. Non-normality. Independent signals should come from non-Gaussian distributions, otherwise the independent component analysis cannot be applied to extract source signals. Complexity. The complexity of the mixed signals is greater than that of its components. Ambiguities of ICA. Ambiguity of sign. The sign of the independent components cannot be determined. In the equation S equals to W transpose into X, if we change the sign of W to the opposite one, the ICA model will not be changed, but only S also have opposite sign. Ambiguity of order. The order of the independent components cannot be determined, that is, the source signals can be arranged in a different way, but the result will be same. ICA pre-processing. Step 1. Data centering. C is equals to x minus mu, where mu is the mean of the mixture signals. Step 2. Data whitening. Decorrelation. Using the PCA, signals are projected onto new axis to have no correlation. For this, Covariance matrix is used to estimate the eigenvalues lambda and eigenvectors v. Then the White signal is obtained as u is equals to vc scaling. To have signals with unit variance, the decorrelated signals are scaled as z is equals to square root of lambda into u. ICA pre-processing example. Create two source signals S1 and S2. Using the mixing matrix A, create mixture signals X1 and X2 where capital X equals to A into capital S. ICA pre-processing example. Step 1. Data centering. Subtracting the mean C is equals to X minus mu. Step 2. Data whitening. Decorrelating and scaling. Z is equals to under root lambda into U. U is equals to V into C. The image shows the original source observations. Each row is corresponding to a single source vector which is 4-dimensional in the example. Measures of non-Gaussianity. Kurtosis. The kurtosis is a fourth standardized moment used in statistics. The kurtosis can be used for quantifying the non-Gaussianity of a probability of distribution function. The kurtosis k of any probability density function is defined as k is equals to e of x to the power of 4 minus 3 into e of x to the power of 2 whole square. Measures of non-Gaussianity. Negative entropy. For a continuous variable, the differential entropy is defined as j of y is equals to negative integral of p of y into log of p of y. By taking the differential measurement of entropy relative to Gaussian, non-Gaussianity can be estimated. J of y is equals to h of y Gaussian minus h of y. J of y is approximated as j of y, which is equivalent to e of g of y minus e of g of v whole square, where v is the Gaussian variable of zero mean and unit variance. The variable y also has zero mean and unit variance, and the function g of is a non-quadratic function. Minimization of mutual information. Mutual information is defined for a pair of random variables. I of x comma y is equals to h of x minus h of x given y. Maximum likelihood estimation. We define a likelihood function as L of w is equals to Ps of w into determinant of w. Find the optimal unmixing matrix W. We need to find the matrix W that maximizes the L of w. Usually, to make computation easier, logarithm of likelihood is taken. Log L of W is equals to sigma T is equals to 1 to capital T log Fi of Wi transpose into x of t plus t into log determinant of W. Independent component analysis is a computational technique used for extracting the source signals from the observed mixture of multivariate signal. ICA can be applied if source signals are independent and non-Gaussian distribution. Also, data needs to be pre-processed to have zero mean and unit variance. Independent components can be computed by three principles: maximization of the non-Gaussianity, minimization of the mutual information, and maximum likelihood estimation. The signals in the time domain there are three sources. S1 of t is equals to cos of 6 pi t into z1 of t. S2 of t is equals to sine of 2 pi t into z2 of t. S3 of t is equals to u into sine of 6 pi t into z3 of t. Comparison between ICA and IVA. Left side shows the product of mixing and unmixing matrices by ICA. Right side shows product of mixing and unmixing matrices by IVA. In the above matrices, the value covered by rectangles to the other values ratio was used to calculate the performance measure. ICA and IVA result 28.5 decibels and 30 decibels respectively. Conclusion: we have extended the conventional ICA problem to multivariate components, which we termed IVA, while ICA algorithm has a single variate score function. IVA algorithm has a multivariate score function which is caused by higher order dependency within source vectors. To model a vector density, we have used scale mixture of Gaussian distribution which models variance dependency. The results have shown that the proposed algorithm successfully recovers the sources not only in a simple example but also real world problem such as frequency domain BSS. Further, researches on various kind of higher order dependency models and multivariate score functions would be important to separate multivariate components.